All right, so here's our example for the type of problem we might see for learning objective 2 of electrostatics. In this one, we use Gauss's law to find the electric field, and it can be for a charge distribution on an insulator or a conductor. And so this problem has a combination of both. We have a solid conducting sphere inside, that's the blue sphere that you see there. It has a radius of r. And it has a positive charge of plus Q. And then around it and concentric with it is a really thin insulating sphere of radius 2r that also has a charge of plus Q. So both of these are going to have a charge of plus Q. And asking myself what I know about conductors and insulators, for a conductor, we know that the excess charge that a conductor has will reside on its surface. And so that means it's all going to be around the outside of this blue sphere. None of that charge is going to be inside the conductor, and because of that, the electric field inside the conductor is going to be 0. The way that I come up with that is I would be using Gauss's law, which I wrote here. But let's kind of go through it in a little bit more detail. So if I'm looking at surface at the range A, where we're looking somewhere within the radius of the conducting sphere, so somewhere in the blue, I would draw my Gaussian surface, and I'm going to do it with red here. I know it's getting small, but we're going to try to use it there. And what I'm thinking about when I'm doing my using Gauss's law is that I'm going to use that red circle represents my surface that I'm using in this integration right here. And so I'm doing the electric field dotted with the area, and then I'm going to look at the charge inside over epsilon naught. Now, because I've chosen that red sphere inside of my solid conducting sphere, I think my electric field should be constant on that and parallel to the area vector. So this could reduce to E times area, where it's area of the surface of that red sphere. But how much charge I enclosed in it is 0, because we already realized that all the charge was going to be on the surface. And this is where we end up with the result that I already stated, but I wanted to show how we did it with Gauss's law, that the electric field inside of the conducting sphere is 0. Now let's do a little bit further out. Let's do between the conducting sphere and the insulating sphere. And let's use a different color. I'm looking at this is my Gaussian surface, the green circle now. That represents a sphere. So again, I start with Gauss's law. And again, I expect the electric field is going to be radiating outward from here, like this. And so my electric field is going to be parallel to my area vector, and I think everywhere on the surface of that green sphere that I've outlined, the electric field will be constant. So it's just E times A. How much charge have I enclosed? I've only enclosed the charge on the conducting sphere, which is plus Q. And then I can say that the surface area of a sphere is 4 pi r squared. Sorry, I should use little r. And that's Q over epsilon naught. So this will change to E equals Q over 4 pi epsilon naught little r squared, which could also be written as KQ over r squared, because remember K is equal to 1 over 4 pi epsilon naught. So what happens is, in this region between the conducting sphere and the insulating sphere, my electric field looks like my charge on my conductor would be a point charge at the very center of the blue sphere. That's what the electric field is going to look like in between the two spheres. Now finally, we're going to look at the region outside of the big insulating sphere. And so that's going to be out here is my Gaussian surface. And a lot of the things that I've done before is going to be the same. And start with Gauss's law. My electric field and my area are parallel to each other. And I'm just going to write this as my R. So this is going to be E times 4 pi R squared. Now here's where I'm going to have a possible change. I'm actually going to enclose the charge on the conducting sphere and the insulating sphere, so that's 2Q over epsilon naught. And so what's going to happen is my electric field in this region is going to be a little bit different. It's going to be 1 over 4 pi epsilon naught 2Q over R squared, which can also be written as K 2Q over R squared. So there's this big difference. Once I get to the surface of the insulating sphere, I'm going to get to include the charge that it has as well. So now I'll have both the Q's enclosed. And so that's what my different electric fields would look like for this problem. So just kind of going with our color coding. This is for the area inside of the conducting sphere. With between the conducting sphere and the insulating sphere, my answer looks like this. And then finally, for the area outside of both the spheres, my electric field looks like this.